Good morning. My name is Varun Saxena. I am an assistant professor with School of Engineering, Jawaharlal Nehru University, and I'm a participant in the refresher course being organized by Dr. Baba Sahib Ambedkar Marathwada University. My roll number is 24, and this is my short micro teaching lecture. Yes. So I decided to give my lecture on nonlinear dynamics. It's a course that I teach in my school. So, as the name suggests, nonlinear dynamics is all about dynamics that doesn't follow the principle of superposition. Since it's dynamics, the motion can be modeled as an ordinary differential equation. And it doesn't matter. In general, of course, dynamics is modeled as a second order differential equation. But even if you have a nth order differential equation that encapsulates the dynamics of the system, this nth order differential equation can actually be decomposed into n first order differential equations. Sorry. Let me illustrate that by taking a very small and a simple example, that of simple harmonic motion. So consider a spring to which a mass is attached. If you give a small displacement to this mass, uh, the particle will go back and forth and will execute a periodic motion. The equation of motion can be written by using Newton's second law of motion. Force is equal to mass into acceleration. If we do that, the final equation that we arrive at is that d2x by dt square is some minus alpha times x, where alpha is a constant given by k by m, where m is the mass of the body and k is the spring constant. Now, since it's a second order differential equation, we need two state variables to decompose them into two first order differential equations. The first differential equation will be in x1 and the second differential equation will be in x2. So we take x as x1 and we choose x2 such that it is the time derivative of x1. So in this problem, if x is the displacement, then x1 becomes displacement and x2 naturally becomes the velocity of the ball. We move further and we can formulate these equations, and that x1 dot is equal to x2 and x2 dot is equal to minus alpha x. If written in a linear algebraic notation, then on the left hand side, you get a column vector with elements x1 dot and x2 dot, which are the time derivatives of state variables x1 and x2. On the right hand side, you get a product of a 2 cross 2 matrix, which we call as a system matrix, and a column vector of state variables x1 and x2. So this is a 2D linear system. The reason why I'm calling it linear is because the highest power of x1 and x2 in this system is 1. Generally, any system that we study in nonlinear dynamics can be mathematically formulated as x dot is equal to fx, where x is an array or a vector of the n state variables. And f is also an array of the functions. And to simplify this further, let me take some examples. So in 1D, this becomes x1 dot is equal to fx1, where fx1 could be any function of x1, linear or nonlinear. Let's say we focus on nonlinear case, so fx1 could be, let's say, minus sine x1. So the equation becomes x1 dot is equal to minus sine x1, and this is a non-linear 1D dynamical system. Another could be x1 dot equal to minus x1. In this case, this is a linear 1D dynamical system. Moving to two-dimensional systems. the equation becomes x1 dot is equal to some function of x1 and x2. And x2 dot is some function of x1 and x2, say g of x1 and x2. Now, f and g are fundamentally different. If both these functions are linear, sorry, then you get a two-dimensional linear dynamical system. And if both these functions are non-linear, then you get a 2D non-linear dynamical system. One important aspect of non-linear systems is that closed form solutions are not always possible, which means that you will not be able to come up with the exact expression for the dynamics of the particle. We are generally in a habit of finding exact solutions, but because the equations become non-linear, it becomes increasingly difficult to find an exact solution. And normally people resort to numerical techniques, which obviously bring in some error. Like for example, if I take a small system, which is dx by dt is equal to sine x, if you integrate it, you will be able to find the exact solution given the initial conditions, which will determine C as given here in the equation. However, systems which are slightly more complex, it will be very difficult to find out the solution. But nonlinear dynamics tells us that we don't really need to find the solutions to understand the problem in hand. So what we encourage in nonlinear dynamics is some sort of a geometrical thinking. Let me illustrate that using a small example. Consider a two-body problem which comprises of sun around which Earth is revolving. Now, this system, if you use classical mechanics, can be very easily deciphered. It is very easy to find out the precise location and velocity of both Earth and Sun. But we living on the Earth are not really interested to know where exactly the Earth is with respect to the Sun, or what is the velocity with which it is revolving around the Sun. For us, what is more important is to know how stable the orbit around the Sun is. If we move slightly away, the life on the Earth is going to end. If the orbit of the Earth starts to decrease and the Earth goes and falls into the Sun, the life on the Earth will end. So the stability of the orbit is a far more important question for us humans living on the Earth, rather than what is the precise location and velocity at a given time, that of Earth. Now, sorry, if I talk about a three-body problem rather than a two-body problem in which you have the sun, the Earth, and the moon, then the Earth is revolving around the sun and moon is revolving around the Earth. Now, this problem cannot be solved. That means at a given point of time, it is impossible to find out the position and velocity of the sun, the Earth, and the moon. But it's not really important for us to do so. What is more important for us to ask is that, are the three heavenly bodies stable in their orbit? If the moon comes closer to the Earth, the life on the Earth will be severely affected. If the moon flies off, the life on the Earth will be severely affected. So the stability of the orbits of Sun, the Earth, and the Moon are more important than knowing their precise location. So nonlinear dynamics provides us with a very different view of dynamics around us. And the most amazing thing about it is that it tells us that we can know a lot about a system and how it works without actually solving for solutions. We look at some different ways of thinking and we can tell a lot about the system. Thank you.